Hello everyone, welcome to the webinar Performance Characterization for RISC-V core using sky130 and OpenSTA, which is a part of my internship program. Now for my case, I had used the Verilog file which is already available with BSD in form of the RB-MIT digital IP. Now the RISC-V, it is a base integer ISA along with its other extension. It can be used for its implementation or for building of the code. Now, the RVME digital IP, it is built using TL Verilog in Makerchip platform, which is provided by Redwood EDA. Now, I had used the already available Verilog file, which was converted from the generated TL Verilog file into the Verilog file, and for that we can use Sandpiper, which is again provided by Redwood EDA. Sandpiper is a code generator which converts the given TL Verilog file into Verilog or standard key system Verilog file. Okay, now how does it does that? It provides a Sandpiper SaaS edition which runs as a microservice in the cloud, and it supports easy open source development and no installation is actually required. And to run locally, we can request for the Sandpiper education edition from Redwood EDA. Now these are the two steps actually we need to generate the Verilog or system Verilog file from TL Verilog. For that we simply need to install the Sandpiper SAS, and then we use the Sandpiper SAS command and provides the input TL Verilog file, and then get the generated Verilog or system Verilog file. Now for my analysis, the PDK which I had been using is the Skywater 130 PDK, which is a joint venture between Google and Skywater with an intention of providing a PDK which is openly available for all. Okay, now it is mature 180-130 nanometer hybrid technology, which was initially developed by Cypress Semiconductor and later it is taken over by Skywater technology. Now the Skywater 130 PDK, it consists of a number of digital standard cell libraries along with the input-output libraries and primitive cell libraries and models. And the default standard cell library is the Skywater high density library, and I had used the timing libraries available with the high density library for my analysis. Now the timing libraries can be found, or it is available in the following part, which is the root PDK folder. Inside the root PDK folder, that is the Sky130A folder, then the libs.ref folder, and then the standard cell library. Under that, the lib library contains all the timing libraries. Now this is the GitHub link from where you can get more information about the PDK. Now let's just go and see the location or the path which I had just mentioned. Okay, for that I had installed the Skywater here, and this is the root PDK, and inside it contains of other two folders, but for us it is we are mainly concerned with Skywater 130A folder, libs.ref, then the high density standard cell library, and the lib folder. Now these are the different timing libraries which are available with the Skywater high density libraries. Okay, now the timing libraries are the event corner libraries, and I had used 15 of the libraries for my analysis. Okay, now for analysis I had used the OpenSTA tool. The OpenSTA tool, it is a gate level analyzer, and as a standalone executable, we can use to verify the we can use OpenSTA to verify the timing of a design using the standard file format, and we provide this file format in the form of a tickle command interpreter, or in form of a tickle file, which is used to read the design, to specify the timing constraint, and to print the timing reports. And also OpenSTA can be used as a timing engine with other tools also. Now as OpenLane uses OpenSTA as its timing engines along with the several other EDA tools which are required for the different stages of the physical design flow. Now more information about OpenSTA, you can visit this GitHub repository. Okay, now for installations of tools, I had actually installed the Open Lane along with the SkyWater 130 nanometer PDQ, which has OpenSTA installations along with it. Now for the installation purpose, I had used the installation procedure provided in this repository, and had also taken help of the free installation course which is provided by BSD, which is available in Udemy. And for Git cloning a particular Git repository, we simply need to use the git clone command and provide the URL of the particular Git repository. Okay. Static timing analysis of RISC-V at different PNR stages. Now, before moving ahead with the topic, let us first discuss what exactly is static timing analysis and what does the static timing analysis do. Now, static timing analysis, as the name suggests, it is associated with the timing specifications of a given design, and it actually ensures or validates whether the proper timing or a timing performance of a design is met for a given timing library or PBT corner. Now, the static timing analysis is actually associated with three different parameters: timing checks, constraints, and libraries. Now, timing checks are the checks which we carry on across the different valid timing path of design, and those checks are usually the setup and hold checks, and then the slew transition check, the load analysis, and the clock analysis. Okay, and the constraints are the specifications which we had decided for the design, and it is given in the form of a standard SDC format. And for our case, we had decided 100 megahertz clock frequency or a 10 nanosecond clock period. And then the libraries are actually used for calculations of the delays of all the cells used in the design. Okay, now as we move ahead with the topic, which is the static timing analysis of RISC-V at different PNR stages, for our case, we had done the static timing analysis for the different stages of the PNR flow, which we had obtained using the OpenLane flow actually. And the analysis which we had done it across the 15 PBT corners or timing libraries, which we had taken from the high density standard cell um, library of the SkyWater 130 PDK. Now, actually, the main aim of our analysis was to check the worst setup and hold slack, and to come up with the best and worst PBT corner of the SkyWater 130 technology, and to verify whether it is according to the trend. Now, this is the flow diagram of our process. In this case, as I said that we have done the analysis for the different PNR stages, and I have already mentioned that we have used the open lane flow. Now, this portion, it actually shows the open lane flow part. In this case, as we have seen, these are the different stages of the PNR flow, and then we had provided the Verilog file for which is used for the analysis. And then after the giving the Verilog file and preparing our design in the open lane flow, then we had run the synthesis, and then the generated synthesis netlist, it is used for analysis across the different PBT corners. What we had done, actually, we had taken the generated netlist from the synthesis flow, and then we had provided the constraint, and we had done the timing analysis for one at a time for the different PBT corners. And based on our analysis, we had come up with the 15 setup and hold slack for the synthesized netlist. And with the result obtained, we had checked the best and the worst PBT corner for the setup and hold slack. Okay, and then we move ahead with the PNR flow, and then we had again taken netlist generated, and done the same thing and check the setups and whole slack, and come out with the best and the worst PVT corners of SKY130 high density timing libraries. Okay, now there's one thing to be noted out here. Now for the static timing analysis or the open lane flow, we have to provide the uh, constraint file for each level of the flow, and we also have to use that for our analysis. Now there's one important thing to be noted is that there's a variable which is the set propagated clock, which has to be initialized before the clock tree synthesis, so that the clock tree is propagated along the across the design. Okay, now so now there and when we will check the uh, timing reports, actually we will see that there is a slight difference in the timing reports, which shows whether a given timing report is a pre-synthesis or post-synthesis report. Okay, and then after routing, apart from the constraints, the set propagated clock variable initialization, we will also get the spec file, and using the spec file, the netlist generated netlist, the constraint, then we again do the static timing analysis across the T-bin PPT corner, and then we come up with the best and the worst PPT corner of a SKY130 130 high density digital standard cell library. Okay, now this is the figure of an of the OpenSTA flow, or actually this figure can be set as the flow for any timing engine. Now as I said earlier, in OpenSTA we have to first read the required files and validate the input. Actually the input should be in the standard file format, okay, which I had already mentioned before. Now in this case, what we have to do, we have to read the required files, and the required files are the timing libraries, the netlist, the constraints, etc. Okay, and then we read the required files, and oh yeah, one more thing, we provide these files in the form of an input tickle flow to the OpenSTA tool. Okay, now after providing the OpenSTA tool and then providing the input and running the STA, we check whether error is there, we run it, and if error is there, we check the error message and fix, and again rerun it. If there is no error and the report is generated, then we basically analyze the setup and whole slack. Now actually there's one thing in this case. What happened, the different libraries which we had provided, it is read one at a time. That is the timing analysis which we have carried out. We carry out the timing analysis for one timing library, and then we move on to the second library and timing library, so on and so forth, until we complete until the all the timing libraries has been used for our analysis. And after that, we move on into the next step in the design flow, and then we move on with the analysis. Now here I just want to mention one thing, like in our case, what we have done, the min-max libraries which we have used, those are the same timing analysis is used as a min-max library to check the setup and host lag of our design. Okay, now let's move ahead. Now, okay, when we talk about static timing analysis, I had talked about timing paths and all those. Actually, these are the important terms which we should know what they mean exactly. Now, these are the timing path, the arrival time, the required time, the hold slack, and the setup slack. Now, timing path, as we know, the timing path is nothing but the path between the start point and the end point. However, in case of STA, we should know which point to consider as the start point and which point to consider as the end point. Now, for static timing analysis, the flip-flop clock pin or the input port is considered as the start point, and endpoint is the flip-flop D pin or the output port. Now let's just see this. Actually, this from this figure, you can see that, as I had said, that the clock pin of a flop or the input port is considered as the start point, and the D pin of a flop or the output port is considered as the end point. Now, based on that, we can see that there are four valid timing path available across this single um, design. Okay, simple design. In this case, you can see there is one the valid timing path across which the timing checks or the setup and hold check can be carried out is this the clock pin of a launch flop and the D pin of a capture flop, and the analysis which we carry across this, it is known as the reg to reg analysis. And actually I have written, it is not visible clearly. And then there is when we do the analysis between the input port and the D pin of a flop, that is known as the into reg analysis. And then the analysis between the input port and the output port, it is known as the into outer analysis. And the analysis between the clock pin of a flop and the output port, it is known as the reg to output analysis. Now, apart from these analysis, we also have other timing checks or setup and hold analysis which we need to carry out. Now, this is the analysis between a flop and clock gate, which is used for providing a clock to the flop. Then this analysis is known as the clock gating analysis. Then there is an analysis between the clock and the asynchronous pin of a flop, and this analysis is known as the recovery or removal analysis. And there is another analysis in which the input of a gate is considered as the endpoint, and this type of analysis are known as the data to data analysis. Okay, then when we consider the flip-flop and latch, there are two kind of analysis which has to be done. These are the time borrow analysis and time given analysis. Now, apart from the timing checks or the setup and hold analysis, I had also mentioned about the different checks which we do. These are the slew transition analysis, and this slew transition analysis, it consists of the data transition analysis and then the clock transition analysis, both min and max. And then for the load analysis, we consider the fan out analysis and the capacitance analysis. And in case of clock analysis, we consider the latency or the skew analysis. And then we then consider the pulse width analysis, which is carried on across the clock pin of the sequential element. Okay, now at this point I want to mention that this figure actually I had taken from STA part 1 course, which is available in Udemy and is provided by VSG. Okay, and for understanding more about this analysis, I think you can check that course. Okay, now let's go back. Actually, that was about the timing part, and I had also spoken about the different timing checks which has to be carried out. Okay, now also the arrival time is nothing but the time taken by a signal to reach at the endpoint, and the required time is basically the timing specification. Here actually I written 1 gigahertz frequency or 1 nanosecond time period, which was actually used as an example in this figure. Okay, and then there is the whole slack. It is the difference between the data arrival time and the data required time, and the setup slack, which is the difference between the data required time and the data arrival time. Now we see that and one important thing is that we want that our slack has to be 0 or of positive value. Now we see that the whole slack and the setup slack, the difference is between the data arrival and the data required time. Now, however, let us see what is the difference between the the whole slack analysis and the setup slack analysis, which due to which we got the definition for the setup slack and the whole slack. Now, in case of whole analysis, what happens? The zeroth edge of the clock, it goes both to the launch flop and the capture flop, and therefore we want that the data arrival time should be greater than the data required time. Now, the data arrival time, it consists of the launch flop network delay plus the combinational delay, and then in case of the data required time, it consists of the hold time. Hold time is the time for the data to be stable after receiving the rising edge. Okay, rising edge of the clock. And then delta 2 is the capture clock network delay, and HU is the setup uncertainty or jitter. Okay, now the difference between the mode of the capture clock network delay and the launch flop network delay, it is skew, and ideally we want that the skew to be 0. Okay, as the same clock goes to the different flops which are available across the design. Okay, and so we want the skew to be as minimum as possible actually. Okay, now this is the for setup analysis. What happens? The 0th edge, it goes to the launch flop, and the 10th edge, it goes to the capture flop. So in that case, what do we want? We want that our data required time, it should be greater than the data arrival time. Now the data required arrival time is same as in case of whole analysis, which is the launch flop network delay plus the combinational delay, and in case of the data required time, it is the time period plus the capture clock network delay minus the setup time or the library setup time. It is the time for the data to be available at the input of the clock, input of the flop, before the rising edge arrives before the rising edge of the clock arrives. Okay, and then setup SU is the setup uncertainty or jitter. Okay, now in this case also delta mod of delta 1 and delta 2 is um, skew, and yeah, delta 1 clock network delay, which is actually the combination of the cell delay plus the network delay, the net delay, and this is also termed as latency. Okay, now this is the difference between the setup and the host lag. Yeah, and in case of whole analysis, the violation occurs when the data required time is greater than the data arrival time. And in case of setup analysis, the violation occurs when the data arrival time is more than the data required time. Right, I had talked about the setup and host lag, which is nothing the tiling checks done during the STA, and then I had also talked about the constraint, which is nothing but the design specifications, and I had also mentioned that the libraries I use for the delay calculation actually. Now in the delay calculation, basically the delay which we calculate is nothing but the propagation delay, which is nothing but the difference in time calculated at the 50% of input output transition, and it is also known as the cycle delay or the rise delay. Okay, now this table, this delay table is generated is generated for an inverter for testing the sky130 PTK for different for TT, FF, and SS corner. Now from this delay table, we can see that the delays of the cell for the FF corners, SS corners, and TT corners are different. For FF corners, the delays are it shows the best delay. The SS corner shows the worst delay, and TT corner shows the nominal delay. And if we and as we now this basically answers why we need to do the static timing analysis across the different PPT corners. Okay, and why and why um, why the design specification met across the different PVT corners ensures that the functionality of a design will be met after the fabrication of the given design. We'll talk about the input file for the OpenSTA. Now, for the OpenSTA run, we want that the terminal should be along the path on which the input file is saved. Okay, and then for OpenSTA run, we simply write the STA command followed by the importable file. And this below figure, it shows the snapshot of the uh, uh, input file. Now let us actually see. Let us see how we do STA analysis. Okay, now let's open a file. We'll do. This is the input tickle file for open STA. Now first we need one read liberty. Now I had made a folder in desktop. Here I have this my liberty files are present in this folder, timing lips, and I'll be seeing the setup and host slack for TT corner. Let's see, read library timing dot, and then read verilog. As I had mentioned earlier, like we had used the OpenSTA open lane run to generate the netlist across the different PNR stages. Now this netlist is also obtained from the open lane run, which I have not included yet. Now this is the netlist after the synthesis. Okay. Now this also we have to. I had already made the tickle file actually, but still let's go through. Okay. Now this is our Verilog file. After that we need to link the design for and the module of the design. Actually it is RVMate. Okay, if you check, it would be RVMate based on the program. This open lane, this basically indicates the module. Okay, after that let's read SDC RVMate .stc. Now these are the input files, I mean the input command in the input file. Now I want to show what happens when we do the report checks command. Now we can we can use the output commands within the input tickle file, or we can directly type it in the terminal. I prefer writing it in the tickle file itself and generating the output. Okay, let's go ahead now. This one, let's save it. I had already made, so let's simply replace it. Okay, so now as I said, the terminal Control-T, or is it Control-Shift-T? Oh, Control-Alt-T, and I was using Control-Shift-T, sorry. Now I said I had made a folder in desktop. Now here it is, CD process variation. If you check here, this is my input ticket file. Now as I said, for OpenSTA run, we simply need to write the STA command. Yeah, first thing is that the terminal path should be along the path where the input ticket file is available, and it is. So now we had to simply run it. Actually, maybe it is not that necessary if we define the path, but I have not tried that, and I won't do that now. Okay, I had only used the report checks command. Now as I said, the report check is actually for the TT corner after synthesis. This is the worst setup select. Okay, now this is the library setup time. This is the pessimism is 0, and then this is the rise edge. For setup, the rise edge comes at 10 because we had taken a 10 nanosecond file, and here so the rise edge comes at this point, and then these are the combinational delay. Okay, now as I said, in this case our clock network delay is ideal because we have not yet done the clock to synthesis. And as I said, we the by default report checks command, it gives information only about the time and delay and no information about anything else. And here the instances, the cell instances. Okay, now if you want to see more information, we can simply type here report checks minus hyphen path delay. I want both the information of the setup and the whole stack, and then I want other information too. I use the field switch, FIELDS field switch, and I need the information about the capacitor, about the nets, about the input pins, and the sleeve. Okay, and then I want the result to be up to 4 decimal places. For that I use the digits switch, and then let's see, here it is. Now we can see it gives information about the capacitance, the sleeve, the delay, the time, etc. Now here we can see the capacitance is around 11 picoseconds, and all those. Our fan out is 3 to 2. Okay, now this is 5 6. Actually, in case of an open lane, the fan out, maximum fan out is 6, so that is maintained. Then okay, the sleeve, this is combinational delay, the combinational delay sleeve, and here this is the arrival time for the combinational delay, this much time it has taken for the signal to propagate from the clock pin of the D flip-flop up to the endpoint is the D plane of the D flip-flop. Okay, and then that, and this is the next rising edge. This is that 10, and then it is minus by the setup line, and we get this is the data required time. And in case of the setup slack, it is data required time by data arrival time. We got this value. And same holds for this. In this case, the value is data arrival time minus data required time. When we calculate the value, it will come to this much. Okay, now there's another thing I want to tell you all. Now so for my analysis, actually I wanted the value, I wanted to store the value in a file. For that, let's see if I have not tried this from the OpenSTA inside. Let's see, suppose if I want to save, we need to use the greater than symbol to write the output into the file. Let's see whether it will be used, it will be done like this or not. Actually it is a shell command. Yeah, it is done actually from inside the OpenSTA. I had not done that. So here this text.report, it got saved. Okay, how about it shows only the max report? Let's see what I have done. Oh, actually I had used the report checks. Okay, sorry, I had used the report checks command, that's why it should give only the max report. Now actually I prefer writing the files inside a folder, because as I had said, we had used the 15 PVT corners for doing the STA analysis. Okay, so what I prefer that my what they call it, my the output should be saved into should be saved at a particular folder. And in this case, let's try that. And I prefer writing the commands in the input ticket file itself. So in this case, report checks minus hyphen path delay min max, and then minus fields tab nets slew and input pins. Okay, now and then finally the digits 4, and I want them to be saved. I have to make a folder outside inside the post synthesis folder. this folder as photosynthesis folder. I'll be using the tt025c1v80 dot report. Let's make that min max. And yeah, I forgot that we can use the report worst slack and min report lowest slack hyphen max. It will give the worst setup slack, and here this I will be writing it in another report as, because I'm not appending the output, I have to take another file for it. So it's okay, not a problem. Setup okay, tt025c1v80. This is max slack dot report, and the same holds for the whole slack. And suppose I need the report total negative slack, which is actually basically comes into picture mostly during the for the setup slack. Okay, total negative slack T report here. Now this will be negative slack, total negative slack, and next I need to create a folder out here as post synthesis. Okay, now let me run it. Exit to move out of STA, and then we run it. Yeah, so I'm done, no error. So if you check in the post synthesis file, we got the tt max slack, min max slack, and then this min max report here. It consists the whole and the setup values. I'll be discussing this report after some time. And then this is the min slack, that means the worst slack min. I made mistake about worst slack min. Let me check. Oh yeah, I had written maximum, that's why the setup slack only is being shown in both the case. So this is a small error. Check it now. Min slack. Now yeah, it has changed. This is the worst slack for whole. Okay, next. This is the total negative slack is 0. That means there is no path with negative slack. Obvious, because we know that the worst maximum slack is 4.12. Okay, now this is how we save and we de-analyze given that list. Now this same procedure we had carried out for the different PVT corners, and based on that we had made a table, and we had then analyzed it later by drawing a graph between PVT corners and the setup slack or the head slack. We'll be discussing about that later. Okay, now before moving to the results section, let us see the snapshot of a timing report along with the various information which it provides. Okay, now from this snapshot we see that the timing report, it consists of the 4 parts: the header part, the data arrival part, the data required part, and the slack part. Okay, now the header part, it consists the start point and the end point, where start point denotes the instance of the launch flop, and the endpoint denote the instance of the capture flop. Okay, and this the path group. The here the analysis is for the clock group, that's why the path group is clock. And then the path type, max denotes the report for setup slack, and the min, it denotes the report for whole slack. Okay, now Then next, as you see, this is the clock rise edge. This is the data arrival time, and in case of in the case of data arrival time, we had the clock network delay plus the combinational delay, and the clock edge which rises, which reaches the clock pin of the launch flop, it is the 0th edge, and the clock flop which reaches the clock pin of the capture flop, it is the 10th edge. Okay, this is as shown in figure. Also, now from this figure we see that the clock network delay, it is ideal. It is the case for the pre-CTS stage where the clock network is not yet propagated in the design. Okay, and then these are the instance or the library reference name, okay, along with the clock pin, and these are the name of the nets. Okay, then here this is the clock network delay which is ideal. Now there is another term, the clock reconversion pessimism, and this clock reconversion pessimism, it comes clock reconversion pessimism, it is also known as the common clock path pessimism or the additional pessimism, and this it comes into picture when the launch flop, then the common clock path of the launch flop and the capture flop, there is a delay difference between them. Okay, now then this is the library setup time, and this is the data required time is this minus the setup time. Okay, and then we had not considered the uncertainty out here, and so it is not shown, okay, in the timing report. And then the slack is obtained by data required time minus the data arrival time, and we get the answer. Now in this case, path type is mint, so it is for the whole. The same explanation goes as for the setup slack. Okay, now one more case. Yeah, I had already mentioned the clock network delay, also known as latency, and here I had shown that. And there is an important thing which I had marked, like the clock network delay, it is ideal in case of pre-CTS stage, and as I had mentioned, there is slight difference in the timing report of the launch of the pre-CTS and post-CTS stage. This actually gives the difference in the clock path. Okay, when the path group is clock. Okay, in this case the clock network delay is ideal, and for the pre-CTS stage, it will post-CTS stage, this will be the difference. Okay, now this actually is the same timing report which I said, which is the post-CTS stage. In this case everything is same except that the clock network delay, here what the clock network has been propagated along the throughout the design. Okay, and in this part the clock network delay in the launch flop plot is this much, and in case of clock network delay for the data required time is this much, and this shows the clock network delay for launch flop of the whole, for whole analysis, and this shows the clock network delay for the capture clock part of the whole analysis. Okay, now in this case, one thing to see is that one thing which I want to mention is that I had used the same min and max library for our analysis, and hence in that case the that's why our clock conversions pessimism is 0. Now there is I had not mentioned in the now after the clock network is propagated, this is how we get the timing report. However, if you want to expand the clock network delay, we can use a switch which is the full clock hyphen format, full clock expanded switch along with the report timing command. In that case the clock network will be expanded as shown in this figure. This is not the entire clock network. Here I have just taken to show the snapshot of the clock to show the clock network delay path. Now this you see, this I had highlighted to highlight the common clock path. In this case you see, now this is the same clock instance which we have used. This is the capture flop path, and in this case here this is the same instance, the same instance, the same instance, and the same instance. And when you check at the delay values for these are same, right? This is 103 picosecond, 90 picosecond, and 99 picosecond, and so the same holds true. And as I said, clock reconvergence pessimism is what? It is the delay difference between the common clock path, and when obviously it's the same delay, in that case the delay difference will be 0. Now however, there is now this actually I am showing, this is how the clock network gets propagated throughout the towards the clock pin of the different flip-flop. Here I have shown only 4 paths. This is the launch flop hold path, this is the capture flop hold path, this is the capture flop setup path, and this is the launch flop setup path. Now in case of setup, launch flop setup and capture flop setup, we see that this is the common path, okay, and in case of launch flop hold and capture flop hold, only the root clock path is the common path. Okay, this was just to show how the clock buffers get propagated in the design. And in case of we basically use a balanced H tree, and in case of SkyWater 130 they use a balanced H tree, and so therefore we can see that the number of delays 1 2 3 4 5 6 7 8 9 10 11, and 1 2 3 4 5 6 7 8 9 10 11, like the number of delays in each part, it is same. Okay, now next this timing report, actually I have shown only the common clock path for the this is the max, this is the capture clock path, I mean launch flop path, this is the capture clock path for the max type, which is for the setup analysis, and this is the common clock path for the launch flop of the whole analysis, and this is the capture clock path of the whole analysis. In this case, you see, like I had used different min and max libraries for the for the static timing analysis calculation. Okay, and in this case we see that as I had used different min and max delay in the common clock path, I had highlighted only the common clock path. These are the common clock path. In this case the delays are different, so in that case what happens, obviously there will be a two different delays along a common clock path is not possible. As you see, this is the common clock path for, if I consider the launch flop setup and launch capture flop setup, this is the common clock path, and in a single path it is not possible to have two different delays, and for that difference in the delays, as I said, we have to somehow remove it, and for that what we do, the delay is calculated, and based on the values of delay we can either remove it from the data arrival path, or add it to the data required path, depending upon like it depends upon us what we want to do. Okay, now this was and this process of removing the pessimism, it is known as the clock reconvergence pessimism removal, or clock path pessimism removal. This was what I wanted to talk about, the timing reports. Almost like at a different BNR stage. In this section, the graphical representation of the setup, obtained setup, and the whole slide with respect to the PPT corner is shown. And then for our analysis that I had already mentioned, I had used the same min and max libraries for tabulation. And this graphical representation is basically for the post-synthesis pre-CTS stage. Now from the graphical representation, in case of setup slide versus PPT corner, we see that the best corner as shown to across the FF corner, and the worst is the SS corner. And in case of whole slack, it is different. The best is across the SS corner, and the worst is across the FF corners. Now again, if we move ahead, now this shows the post CTS results. In this case, the setup and the setup versus PVT corner shows a similar trend, that is the best corners are towards the FF and the worst corners are towards the SS. And in case of whole stack, the same thing, the best corners are SS corners and the worst are SS corners. And then this is the post CTS post layout. Here in this case also the post for post CTS also we can see in case of setup slack, the best the best corner are the FF, and the worst corner are the SS. And so also for the whole slack, the best corners are across the SS and the worst are across the FF. Okay. Now, also we had done a net gate analysis of a basic design. In this, the design comprised of the launch flop, capture flop, and a combinational delay. Now, in this case, what we have done, we have checked the delay of a NAND gate and the input sleeve with respect to the different PBT corners. And this graph shows the trend. Now, in this case, we can see the PBT with respect to the PBT corner, the cell delay is best towards the FF corners and is worse towards the SS corner, and input sleeve also holds the similar trend. And in case of the NAND gate delay obtained during the whole analysis, in this case also the cell delays shows the best value across the FF corner and the worst value across the SS corner, and the input sleeve also follows the similar trend. Now, based on our analysis of the STA of the RISC-V using for the different PNR stages, and then delay analysis of a basic design, we can say that for in case of the setup slack, the best corners are the FF and the worst corners are the SS, and in case of FF, the best corners are the SS and the worst corners are the FF. Now from the post layout result, I am showing the setup slack of the TT corner, which is around plus 368 nanosecond, 154 megahertz clock, and then the corner for a clock of 10 nanosecond, and the worst setup slack across across SNN 410 1V28 is minus 47.93 nanosecond, and the best FF corner shows a slack of 6.29 nanosecond. Now, whole slack, I am not shown here actually. Whole slack is worse across the FF and the best at across the SS corner, and with respect to TFT, the whole slack shows a value of 0.17 nanosecond. And then for future work, I have to actually in my analysis actually, I was basically stick to the basic reg to reg analysis, and there are different other checks which need to be done, and for that I had used the I will be doing the STA for all other checks, and then the multi-mode multi-corner analysis, as I had used the same library. In this case, I'll be using the different library, different min and max library, and then optimizing the particular file for OpenSTA. As I had mentioned earlier, in OpenSTA we had taken one library at a time for analysis, but now I want to I will optimize the input ticker file so that we can loop actually the liberty file, and then we can save the generated output in the respective folders. And then I'll have to study about the timing violations and the echo and perform echo, and then the performance characterization of the base VSD PB SOC, which was the main agenda of the internship. Okay, then now with respect to reference, these are actually the links which will give you more information about the about my work. The VSD PC VRD, it is the main GitHub link at which I had. This is this one actually. This is the main GitHub link. Okay, from where you will get the information about my work. Okay, and then there are the other GitHub links. This shows the CMOS circuit, CMOS design spice simulation using sky130, from where I had taken the delay table, and then the RISC-V mixed workshop, from where I had taken the Verilog file, and this is the workshop which I had attended. The details of the workshop which I had attended, and then the open lane workshop for the advanced open lane workshop. I mean, for the open lane course, I had followed this link. I would like to thank Kunal Ghosh sir, my mentor, for his guidance, his assistance, his understanding, his patience, and for allowing me to get diverted most of the time, and also channeling my thoughts in the proper direction so that I get the answer to my questions, and then also to actually nullify the root cause of the diversion. And then also Without his assistance and guidance, it would have not been possible for me to reach at this stage of my internship program. And also, I would also like to thank him because with his courses and then the workshops that I had attended and IGTP program I am going through, it has really actually helped me to move ahead in the VLSI domain. I feel like yes, now I understand the different scopes actually which are available, or different types of profile which are available in the VLSI domain. Thank you for that. I'd also like to thank Tim Edwards sir for actually guiding me to the timing libraries which are available with the Skywater 130 PDK. I'd also like to thank Shivani Shah because her work, the Verilog file which I had taken, it was from her repository, and it is because of her work that I can reach to this stage. Otherwise, reaching this stage would have taken a much longer time. Okay, and then Steve Hoover, sir, I would like to thank him for his because he's the main person behind the RISC-V. And also, without the workshop, that is another thing. It would have taken a much longer time because I would have needed time to understand about the RISC-V core also. And then I would like to thank Anagha Ghosh ma'am for her assistance in all the issues or which I face with, which requires her help. Thank you for that. And special thanks actually to Kunal Ghosh sir, Anagha Ghosh ma'am, and to the entire BSD team to for this online BSD HTTP program, because I think if it would have been, if it would have not been online, I would have never reached for the internship. Thank you so much.